Hello, welcome to my video series of algorithms. This is part 6 of Module 2, Logic and Proof. In this video, we will discuss some basic proof techniques. From the previous videos, we have learned the basis of constructing proofs. We know that each sound proof must contain two important components. They are the true premises and valid argument forms. Using this basic rule, we'll be able to construct our proofs. In addition, there exist some commonly used proof techniques. Learning these techniques may make it easier for us to construct some proofs. In this video, we will introduce 5 proof techniques. They are proof by exhaustion, proof by division into cases, proof by example, disproof by counterexample, and the generalization of a generic particular. We will first introduce the basic idea of each technique, and then give a concrete example for each one. The first technique is proof by exhaustion. By its name, it considers every element in the domain and shows that it satisfies the proposition that needs to be proven. When we have picked a specific element, we will be able to obtain more information regarding the element. Such properties will make the discussion of the proposition to be proven much easier. However, this technique only applies to propositions with small and finite domains, as we need to exhaust all elements in the domain. Let's look at the first example. Prove that for every integer x, where x is between 4 and 10, it can be written as the sum of two primes. The key to proving the proposition is to notice that it has a small and finite domain. In other words, we only need to discuss the cases when x takes values between 4 to 10. In this case, we can discuss each possible value for x. When x is 4, we know it can be written as the sum of two primes. That is, as the sum of 2 and 2. When x is 5, it can be written as the sum of 2 and 3. When x is 6, it is the sum of 3 and 3, and so on. Eventually, we have discussed each case. We can claim that when x is between 4 and 10, it can be written as the sum of two primes. The rule of inference we applied in this proof technique is universal generalization. That is, when we have shown that every element in the domain can make the proposition true, then the proposition is true for all elements in the domain. The second proof technique to discuss is proof by division into cases. This technique is similar to proof by exhaustion in that they both break down the entire domain before discussion. A smaller domain usually means additional information. For example, imagine we break the large domain of integers into two smaller domains, the even numbers and the odd numbers. Then, when we discuss the smaller domains, we can include their additional properties of being even or odd. The difference between proof by division into cases and proof by exhaustion is that proof by division into cases can still discuss an infinite domain, while proof by exhaustion discusses a specific element. For example, the subdomains of even and odd numbers are both infinite. Therefore, unlike proof by exhaustion, proof by division into cases can be applied even when the domain is infinite. Let's look at this example. Prove that the absolute value of x times y equals the absolute value of x times the absolute value of y, where x and y are real numbers. The key to proving the proposition is to eliminate the absolute values, which complicate the discussion. To eliminate the absolute values, we need to know whether x, y, and their product are negative or non-negative. In this case, we can use proof by division into cases. We know that x can be non-negative and negative, and the same to y. Therefore, we need to discuss 4 different combinations of the values of x and y. For example, we need to discuss when x and y are both non-negative, both negative, or x is non-negative and y is negative, and x is negative and y is non-negative. Under each specification, we'll be able to eliminate the absolute values and prove the proposition. The details of the proof are shown in this slide. The rule of inference used in this technique is also named as proof by division into cases. That is, P or Q, P implies R and Q implies R, then R. The third proof technique is proof by example. This technique is useful when we are trying to prove an existential statement. In this case, we simply need to identify an element in the domain that can make the proposition true, and we can claim that the existential statement is true. Consider this example. Prove that there exists an integer that can be written as the sum of cubes of positive integers in 2 different ways. Note that we are only asked to prove the existence of such an integer. In this case, we can use proof by example and propose an element in the domain that makes the proposition true. Using some computer search, we can find such a positive integer. Therefore, we can claim that the corresponding existential statement is true. The rule of inference used here is existential generalization. The fourth proof technique is disproof by counterexample. This technique is similar to proof by example in a way that both need to identify a single element in the domain. However, it is used to disprove a universal statement. For example, show that for all integers x and y, if x squared equals y squared, then x equals y is false. Note that the proposition is a universal statement, which says that all elements in the domain should satisfy the proposition. To disprove it, we only need to provide an element from the domain and show that it does not make the proposition true. In this example, the domain of x and y are integers. Therefore, using this proof by counterexample, we'll let x be -1 and y be 1, which makes the proposition false. In this case, we can claim that the corresponding universal statement is false. The logic behind this proof technique is similar to proof by example. That is, by providing an element C which makes PC false, we can claim that there exists some x that makes Px false. Then, by De Morgan's law, we can claim that for all x, Px is false. At last, we'll discuss the fifth proof technique, generalization of a generic particular. We have discussed how to prove an existential statement and disprove a universal statement before. However, in many cases, we need to prove a universal statement or disprove an existential statement. Making such proofs requires us to discuss every single element in the domain. For example, when proving a universal statement, we need to show that each element in the domain can make the unquantified proposition true. When disproving an existential statement, we need to show that every element in the domain makes the unquantified statement false. If the domain is small and finite, we can use proof by exhaustion to discuss each element in the domain. However, the domain could also be large and infinite. In this case, we'll use the technique called generalization of a generic particular. The technique contains three main steps. First, we would like to select an arbitrary element from the domain. As it is selected, we'll consider it as a particular element and call it the particular. Then, we shall discuss whether the particular can make the unquantified statement true. Note that during our discussion, we should not include any property other than those shared by all elements in the domain. For example, when we pick a particular C from the domain of integers, we should not assume that x has any properties other than being an integer. This is because it is the only information we can confidently assume for the elements of the domain. In this case, we say that the selected particular is a generic particular, as it only has properties that are generic to all elements in the domain. Finally, after discussion on the generic particular C, we will generalize the conclusion to the entire domain. We can do this because all properties we have used during the discussion are generic for all elements in the domain. Let's look at the last example. Show that for any real number, after a series of operations, we'll get 7. Note that here, we need to prove a universal statement, and the domain is real number, which is infinite. In this case, we can use the generalization of a generic particular technique. We will first pick a particular, say x, from the domain. We assume that it is generic, or that it has no other property than being a real number. Then, after applying the series of operations on x, we get 7. Because we have not used any additional property other than assuming x to be a real number, we can generalize the conclusion to the entire domain. Finally, we can claim that the universal statement is true. The rule of inference used behind this technique is universal generalization. And by using De Morgan's law, we can also use the technique to disprove existential statements. In summary, we have introduced 5 proof techniques in this video. Most of them try to provide direct evidence for the proposition. Therefore, they are called direct proofs. In the next video, we'll introduce several indirect proof techniques. Thank you for watching, and see you next time.